Thank you very much. Let me thank the organizer for bringing us all together, and I'm very pleased and very honored to be uh, able to give a talk here. So I will give. It is about a joint work with John Gong from University Wisconsin Madison, and it's about. I hope it will work. Ah, yes. So the problem is a kind of geometric problem, holomorphic geometric problem, and at the end it will boils down to the kind of dynamical system kind of. So you are taking a complex compact manifold C of any dimension, and so you would like you embed it into another complex manifold. So you don't care about exactly what is the codimension. It could be different kind. And you would like to compare somehow the neighborhoods of this embedded neighborhood of the embedded complex manifold. So first of all, you would like to know whether you have a neighborhood of C into M, which is biolomorphic equivalent to the neighborhood of C into M tilde. Okay, so it means that you have a biolomorphic map that will that will fix the manifold C, and that will send the manifold neighborhood to another neighborhood. And in my problem, it's kind of germs of the neighborhood, so I don't care about the size of it. Okay. So I should say that once you have one embedding, you have another one for free, namely the embedding of C as the zero section into the normal bundle. So it makes natural somehow to compare as a first approximation the embedding of C into M with the embedding of C into the normal bundle. So it was this kind of problem was raised in the 60s by Grauert under the name, and it is known under the name of formal principle, to say that if you have a formal equivalence, meaning that you don't have obstruction, in other words, you have an equivalence of the jet of any jet of the neighborhood to the same jet of the other neighborhood. And so you would like to know whether, if it is you don't have any obstruction, whether it gives you a genuine holomorphic transformation. So it happens that when you are negative, if the normal bundle of the embedding of the normal bundle is negative, in some sense that I will not uh, explain now, then it's always the case. And so you have a kind of rigidity. So in other words, rigidity means that in the neighborhood of C into M, you don't have any other perturbation of C in that. So this was done by Grauert in the 60s for hypersurface, and this has been generalized by Hironaka and Rossi for higher codimension. On the other hand, there is a similar phenomena when the normal bundle is positive, which means that the adjoint of the normal bundle is negative. And you have a kind of similar problem, a bit less, so it's not that precise, but it says that if the jet of the two embedding are the same up to some finite k, then the neighborhood of are effectively holomorphically equivalent. Okay, so before in Grauer's situation, you just need to look at the normal bundle. If it is negative, then automatically you don't care. If it is formal, here you just need that you have equivalence to to a finite order jet. So it's a kind of finite determinacy, if you wish. And so this has been nowadays also reworked by Jumuk Wang. And there is also another kind of problem which are very related, but I will not go to that today. Is a work by Ueda and also by Koike about the existence of an holomorphic foliation in the neighborhood of C without singularity. So it's the same kind of problems to some extent. And so, well, the geometer thought that as soon as you have a formal thing, then you have a convergent thing, as in Grauer's situation. And then another guy, Arnold, Vladimir Arnold, came and say, okay, guys, there is some problems. And he said, okay, I construct an elliptic curve that is a torus, if you wish, dimension 1, embedded into a complex surface. And he showed that this embedding was equivalent holomorphically to a neighborhood of the zero section in the normal bundle if there is some kind of condition like Diophantine condition that you encounter in dynamical systems. So people thought that it was really a completely different kind of phenomenon. And I don't give the definition of Diophantine property because I will go to that a bit later in a more general setting. So it was a kind of, and in the situation of Arnold, it's not negative nor positive, it is flat, which means that the transition matrix of the normal bundle is constant. Okay, so it does not depend on the point. That was quite different. So it means, roughly speaking, that to some extent, that you can use kind of geometry using curvature property in the negative and positive situation, and you understand what it goes, how it works. But in the flat case, you need other kind of methods. And those methods, they are coming from dynamical systems. And I will pursue this with Gong. We will pursue this kind of ideas. So this has been generalized, the work of Arnold by Ilyashenko and Kjartli, to the product of elliptic curves, okay, to certain product. And so in some cases where the normal bundle is a special kind. And we will, so with Gong, we worked some years ago in a general framework in order to give a general statement that is somehow difficult to apply effectively because it depends on the the transition function of a covering of the normal of the neighborhood. Okay. So here we will do something completely different in order to handle a problem which is more specific. So now is the theorem that we will I will prove in that setting. So now we are considering C as a general complex torus. Okay, so it's not an elliptic curve, so it's more general, any dimension, and it's not a product of one-dimensional torus, any kind. Okay, so this is C, and it is embedded into n plus d dimensional manifold. So you have you assume that the tangent bundle is split. It is you have a direct sum between the normal bundle and the tangent to C. Otherwise, you see, it's you look at the transition matrix. It is a block. You assume that it is a block diagonal matrix. Then what we say is that there is an holomorphic equivalence between that neighborhood, or even a smaller one, to a neighborhood of the zero section into the normal bundle, provided that there is two conditions. First of all, that the normal bundle has Hermitian transition function. So flat Hermitian. So it means constant and Hermitian. And the second is that the normal bundle is non-resonant Diophantine. I will explain what it means in a second. So this is really kind of a dynamical system property that involves, say, the normal bundle object, and also involves the torus, the way the torus is defined. Okay. So here, first of all, how we define the torus. The torus we are playing with is Cn quotiented by a lattice generated by 2n numbers. So you take n of them, which are the unit vector of Cn, say, okay? And you have the other one, tau1, tau n, which must be satisfy some condition like that. So if you have only one, if you had just classical torus, you have E1, and you have that vector, and it is this, with this that you, this is tau1, this is the way you construct the torus. And so we do that for a general one. Okay, so now we are starting to play our game. So there is some kind of geometry setting to state, and from that I will translate the problem into a kind of dynamical kind of problem. So we have C, and there is a covering here. Okay, so there is several covering, but I will take a special one. And so you have the embedding into that one and the embedding of C into the normal bundle. And so you take the covering map of all of them. And okay, so everything is defined by the pi1, fundamental groups. And what you have is that the two neighborhoods, say M in C and M in C, C in M prime, they are equivalent if there is a covering transformation sending the covering into the other one, the neighborhood of the covering into the covering, the neighborhood of the other covering, fixing pointwise. So that's the property. And so one of the main results goes back to Hsu in the 70s that says that if C tilde is a Stein manifold, which is embedded into another one, another manifold, then there exists a neighborhood of it which is biholomorphic to the neighborhood of the normal bundle, of C into the normal bundle. So that's a... I'm not sure. I think it is in Hsu. Maybe... yes. Yes, okay, yes, that's it. Okay, thank you. And so what you will do, you say, okay, you have the two coverings there, and so you say that this one is biholomorphic to the normal bundle there, and you say that this one is biholomorphic to the normal bundle there. That's the very beginning of the setup. Okay, and what we prove, which is not difficult but not completely obvious, is that if you cover the torus by a cylinder, namely this guy, which is a Stein manifold, then the pullback of a flat vector bundle of C on C gives rise to a holomorphically trivial vector bundle on the covering. That's not completely obvious, but that's not so difficult. And so you see what's going on somehow is that, well, we have assumed that the normal bundle is flat of the embedding. You will cover it by a cylinder, okay, just like that, which is a Stein manifold. And then you will have to pull back the this normal bundle, and this normal bundle is holomorphically trivial. And so at the end, you obtain that kind of things. So this normal bundle is trivial, so it looks like this. This normal bundle is also trivial, and it looks like that. And so finally, the problem we have to deal with, more down to earth, is the following. Is the quotient of this space by the deck transformation obtained there, the automorphism of the covering, is biholomorphic to this guy quotiented by the deck transformation of that covering. That's what it boils to. Okay? And it's the problem that we will have to solve. And finally, we know somehow that the deck transformation here, they can be described as a kind of linear map. And the deck transformation of there, they can be described as nonlinear perturbation of the linear map. And so finding this problem amounts to find a transformation that will linearize somehow the deck transformation of that one. So here is a more technical description of it. So what you will have is you have the deck transformation. You have n of them because you are on the cylinder. So and the lattice was 2n dimensional. So you have n deck transformation. This is the deck transformation of the normal bundle or the covering of the normal bundle. And of course, they are pairwise commuting. That's because of the pi1. It's like that. And so you can write the deck transformation as a perturbation of this guy. So for me, V would be the normal directions, say, and Z would be the tangent direction. And so I need to remove somehow this kind of nonlinearity at the end. What is tricky here is the domain of definition of all those maps. You have to find a neighborhood that describes correctly the torus, okay? And so you end up with some functions which are a bit tricky to deal with. And so, of course, as I assume that NC is a constant Hermitian transition function, so, and you have an abelian group, so you can diagonalize them simultaneously. And that's what we do here. They can be diagonalized simultaneously. Yeah, sorry? Why they commute because of the pi1. You are on the cylinder. It's a... And so finally, you do some change of coordinate like that. And so those numbers, lambda I, lambda ln, they are given by the vector of these vectors, okay? And m is given by some number that describe the normal direction, the normal bundle. And so you define the transition, the deck transformation of the normal bundle to be given by such a map. So it's a linear one in V, okay? And H now plays the role, is written by this kind of. And so Yes, so here is a description of the kind of domain we have to deal with. So it's a bit complicated to figure out. So you have the two n vectors here, and so there are one periodic in the n first coordinate, the function we are dealing with. And so finally, by replacing z by h, you end up by a holomorphic function in the neighborhood of that kind of domain. So this is the normal direction, and this is the neighborhood of the torus somehow. It is given by this kind of thing. So these are Renard domain and so on, but you need to do some calculus on that, like Cauchy transform and so on, Cauchy estimate and so on, which are a bit non-standard on that kind of domain. Okay, so you are dealing with holomorphic functions which are one periodic in the first two coordinates, and so at the end, okay, so now we are going to the problem. So you need to somehow linearize. So you have tau I, which is equal to tau I hat h of v plus higher order term in v. Okay. And so those, as I said, this is equal to, I forgot what was the notation, so Li of h, Mi of v plus higher order term. And so in order, you would like to find a transformation that satisfies something like that. This will be the transformation that will transform this, this nonlinear perturbation of tau I to its linear part. Okay? And that will serve as an equivalence between the neighborhoods for the deck transformation. Okay? And when you do that, if you do that order degree by degree, say, with respect to this, there is one, the linearized operator of this looks like that kind of operator. Yeah. So you have to deal with the u evaluated at this. So it just, I should have done this in the opposite direction, say, it doesn't matter. And you see that this part would be coming from this part, and the first part of this will give you someone like that, the linearized part. Okay? Because this is tau I hat plus higher order term. So if you compose it by f, the first term that you will get will be tau I times this, okay? Which is precisely this kind of guy that you will have. And so if you write down in coordinates what this means, well, you will end up with precisely this kind of numbers. If you have, I should write it now. If you have, say, HP VQ, P is in Z, N and Q is in ND. And if you compose this by EI, no, what's the L, sorry, LIH MIV, this gives you precisely lambda ij, lambda I to the P times mu to the Q, mu I to the Q, and the same monomial here. And this means lambda I to the P means lambda I1, sorry, I1, P1 lambda I n Pn. Okay? So you can easily see that you have that. And the Diophantine condition we define says that these numbers, they don't accumulate zero too fast when p plus q goes to infinite. Okay? It's a number. There exists, so sorry, that's a good question. There exists, I should have said, there exists a d and there exists a tau such that for all qp, you have this kind of inequality. Okay? And this kind of inequality appears because if you want to solve L of u is equal to something, well, you make the expansion in terms of this, and you take the coefficient of the right-hand side, and you just need to divide by the number that appears in like that. And these are the numbers. And of course, you have a overdetermined system. You have a n equation with one unknown, and you take the best. That is, you divide by the biggest number to be on the safe side. Okay. So now you are supposed that you have a biolomorphic mapping from a domain. So there should be an epsilon here somewhere to the image of the tori in the epsilon. You are supposed that they are pairwise commuting. Okay, that's the problem I'm starting with. And you assume that there are perturbation of tau1 hat, tau1 n hat, that is Diophantine in the previous sense. Then finally, there exists a biolomorphic map F that will satisfy this. In other words, you have one transformation F that will conjugate simultaneously tau I to tau I hat. In other words, you have linearized the deck transformation here, like that. So the way to do that is a kind of KM method that is Kolmogorov-Arnold-Moser. So it's a kind of, say, how do you say, Nash-Moser scheme. In other words, what I want to say is that if you assume that tau I is equal to tau I hat plus, say, something of order k, then you do one transformation, fk, tau I fk inverse, so that you would have tau I hat plus f epsilon 2k. So you are doubling somehow, you make a square of the discrepancy to the original one. That's the kind of Nash-Moser kind of. So it is, oh, sorry. So it is what is written here. So you're doubling. And so you can prove that it converges this way. So it is really the kind of things that are occurring in dynamical system where you need to linearize some mapping by a neuromorphic transformation. What is quite different, so what is classical in dynamics is when this guy does not depend on H variable. So it doesn't depend only on the vertical. So you have a power series. And okay, so this is the classical thing. Now here it's a bit complicated because it involves the dependence on the torus. You have to take into account, and you have to make transformation on the torus as well. So that makes the life a bit difficult. And so one of the key propositions is this kind of things that, okay, you have to, it's a kind of co-cycle condition, let's say a compatibility condition, if you wish, that at some point, if you're given Fi as a good holomorphic function somewhere, and that satisfies this kind of compatibility condition with the operator that was written somewhere before, then you can effectively find a G, a solution that solves simultaneously all those equations. So, okay, so you are given right-hand side Fi that satisfies this compatibility condition on the intersection domain. Then you can find a genuine solution to the kind of problem, but defined on a smaller domain. So you have what is usual, you have to reduce you have to shrink the radius, but you need to shrink a little bit the neighborhood of the torus, the way you define it. And so not only you have a solution of this, but you have estimate. And this estimate goes like that. So you can estimate the solution on a smaller domain by the max of the right-hand side on a larger domain. And here you have to divide by something that's related to the amount of discrepancy that you have. And the tau is the same that is defined from the small divisor problem. And the nu is something that comes from the geometry of the torus. So it's a bit complicated to define, and I will not do it. And so this is defined there, and also this one is defined also there, and it satisfies this kind of property. And okay, so yeah, sorry, yes, sure. So it is an existence. There exists a function G. Oh yeah, sure. The kappa is fixed. It's a fixed number. Sorry, thank you. No. It is a fixed. It's a fixed number. So thank you. Sorry, I was a bit sloppy. Yeah. So the kappa is a fixed number that is given by the geometry, as well as the nu. So and there exists C prime. The constant here does not depend on the F. And yes, I think that's it. Okay, so you have a way to define a common solution when you have a compatibility condition, but you have to shrink a little bit. Some amount. So I didn't say that delta should be in such a way that epsilon minus delta over kappa is positive, but this is something that you and so with the help of this kind of estimate, you can still measure the solution step by step, so to speak, keep track of those. That's not completely obvious. And yes. So yes, so I'm just giving you this slide just to show you the way it works. I mean, the way you compute. Now, after that, you need to estimate something else. So you need this kind of things tell you that you have compatibility condition because they are commuting pairwise, and the solution that you are given is something like that. Okay. And so you have to truncate with the degree of higher and higher. I think I will stop there. Yes, thank you for your attention.